In the previous class we have seen compressed hydrogen tanks. Depending upon what material they are made up of, they were divided into type 1, type 2, type 3 and type 4 tanks. Type 1 were all metallic, type 2 with an inner metallic liner and hoop wrapped with fiber resin composite, type 3 where there is metallic liner and a fully wrapped fiber resin composite, and the type 4 tank which had an inner polymer liner with an outside carbon fiber composite. So, this is what we have seen in the previous class. In a type 4 tank, this is an inner liner which provides the gas tightness as well as reduces the permeability. Then there is a carbon fiber composite, there is a carbon fiber wrapping and thereafter a resin. Now, this composite provides strength to the tank against the environmental challenges. Now, this tank, other than the carbon fiber and liner, there are other components like a port which is having a Bosch here, a port which has a valve, and then there are several other accessories which are there with the tank. This is like the in-tank regulator. Then there are pressure sensors to measure the pressure. Then there is interfacing with the refueling station for filling in, at the same time for dispensing, for releasing the hydrogen for the utilization purpose. Then there are thermally activated pressure relief devices. So, refueling port, vent line port. So, all these accessories are there other than the remaining accessories outside the tank which are like the tubings, other valves, flow regulators. So, all these are the components of the type 4 tank. So, today we will look at the liquefied hydrogen storage. Now, by liquefied hydrogen storage we means like the temperatures are in the cryogenic range. Now, the cryogenic term itself was coined from a Greek term and that means ice cold. Now, here the temperatures are below minus 150 degrees centigrade and the gas in the process, the gas at ambient conditions is cooled down to temperatures which are cryogenic temperature and at ambient pressure. Now, if we look briefly onto the history of liquefaction, it started way back in 1812 when Michael Faraday, he carried out certain small scale experiments in a test tube to experiment with the different gases to liquefy them, and he was successfully able to liquefy ammonia and carbon dioxide. In 1840, Gauri, he was able to produce ice by means of air expansion engine. In 1844, there were experiments being carried out on large scale for liquefying gases, and that was by Trelorer, and he used mechanical compressor for this purpose. In 1845, with the use of hydraulic pump, large quantities of liquid and solid carbon dioxide was produced. Now, the major landmark in the history of liquefaction was the invention of Joule-Thomson effect, that was in 1852. Thereafter, Kirk, he came up with the Stirling cooling system in 1860. 1863 was another landmark when critical temperature was introduced at that time. Thereafter 1877, Pictet and Calitet, they individually were able to produce mist of liquid oxygen. This was not completely liquefied, which was later on completely liquefied in 1883 by Wroblewski and Olszewski, and they liquefied oxygen and nitrogen. So, Wroblewski, he liquefied, and Olszewski, he confirmed that liquefaction by the process which was given by him. In 1884, Wroblewski, he created mist of hydrogen, and again he confirmed. It was another landmark, that was in 1892 when Dewar, he developed the vacuum insulated vessels for storing cryogenic liquid. and thereafter came the term 1894, the cryogenic term was coined. In 1895 Lind he patented the air liquefaction using expansion valve, and then he started producing the various gases at industrial scale. He also established the well known company for liquefaction, Lind. In 1895 started the recuperative heat exchangers, and that was first time introduced by Hampson. In 1898 Sir James Devore he liquefied hydrogen, and that was in a very small capacity liquefaction device. In 1902 Claude he developed a system which was for air liquefaction, and that used expanders, and he also established a company which is now also known as Air Liquide. In 1908 Owens he first time liquefied helium, and 1910 onwards there were large sized liquefiers which were constructed, and thereafter large capacity applications where large capacity of liquid hydrogen and oxygen is used were developed after 1930. So, we can say that in the period 1850 to 1900 the thermodynamics of liquefaction was developed, while in the period 1900 to 1950 the various technologies for liquefactions were developed, and thereafter started the large scale production of these liquefied gases. So, this is how the cryogenics, liquefaction of various gases have advanced in past. Now, coming back to liquefaction of hydrogen, in liquefying hydrogen there are several challenges involved. The first and foremost is, we know that, and we have also seen thermodynamics of hydrogen liquefaction in earlier classes, that the liquefaction of hydrogen can be done by reducing its temperature to 20 K, minus 253 degrees centigrade, and this is a very low temperature for liquefaction, requires a lot of energy. The another challenge is ortho to para conversion, and this conversion has to be occur, and at the same time this conversion is exothermic. So, we have to also remove the heat of conversion from the process of liquefaction. And the third major challenge that lies is that the inversion temperature of hydrogen is below ambient temperature. This we have earlier seen when we have studied the thermodynamics of expansion, the Joule-Thomson effect, what is the Joule-Thomson coefficient, when it is positive, then if it is positive, in that case with the reduction of pressure temperature also reduces, that means with expansion cooling is observed. If it is negative, reverse of it happens. That means if the expansion occurs or pressure reduction, then temperature will increase. Joule-Thomson coefficient which is negative at ambient temperature, and in order to cool it down, we have to cool down below the inversion temperature so as to use the throttling process. So, these are the three major challenges which are observed in hydrogen liquefaction. Now, if we look these challenges one by one, the major challenge is the ortho to para conversion. Now, this was in 1912 that while measuring the heat capacity of hydrogen, it was observed that the warming and the cooling curve, they have shown a hysteresis, and that hysteresis, it was proposed in 1927 that it was arising because of the two different spin isomers of hydrogen, and this presence of these two spin isomers was experimentally proven in 1929. Now, what this conversion is, what these spins are. So, if the two spins, the nuclear spins, proton spins are parallel, then it is ortho hydrogen. If however the two spins are anti-parallel, then it is para hydrogen. Now, there is a difference in the calorimetric properties of ortho hydrogen and para hydrogen. At the same time, the energy levels of these two isomers are also different. So, ortho hydrogen is an excited state, it is in a higher energy state compared to the para hydrogen. So, when we are liquefying hydrogen, this conversion which occurs ortho to para hydrogen, that extra amount of energy is released in the process. Just to explain in more detail, the normal hydrogen which is under ambient condition, at the ambient normal temperature pressure condition, it consists of 75% of normal hydrogen, consists of 75% of ortho hydrogen and 25% of para hydrogen. However, during liquefaction at the boiling temperature, at the boiling point of 20 K, the equilibrium composition of hydrogen is 99.8% of para hydrogen and the remaining is ortho hydrogen, and that is the equilibrium composition at its boiling point. That means if we are reducing the temperature of hydrogen, in that case the ortho hydrogen, which was 75% under normal condition, has to convert in such a way that we get 99.8% of para hydrogen from the normal hydrogen, that is the equilibrium hydrogen. Now in this conversion process, since ortho hydrogen is in higher energy state, so the excess energy is released, thus the process is exothermic process. So this release or this conversion of ortho to para hydrogen, this is an exothermic process, and that heat which is released, that needs to be removed during the liquefaction process. Now if we see the concentration of para hydrogen with temperature, we can see that it has a very strong dependence on temperature. However, it has negligible dependence on pressure. So there is a strong dependence on temperature, specifically we can see in this region, but no pressure dependence. Now when we want complete conversion of hydrogen from the ortho to para, so from complete ortho to complete para conversion, that releases heat, that releases energy approximately 703 kilojoule per kg. However, normal hydrogen, which is 75% ortho, 25% para, when converts it into equilibrium hydrogen, then the amount of heat which is released is 527 kilojoule per kg. Now we can see that both these energy is higher than the latent heat of vaporization for hydrogen, which is 446 kilojoule per kg. Now that means when we are converting, when we are liquefying, when we are reducing the temperature of hydrogen, this amount of heat which is released in this ortho to para conversion is sufficient enough to evaporate certain amount of liquid hydrogen as well. So because this latent heat of vaporization is less compared to the heat released during this process. Now this process wherein the stored liquid which contains ortho hydrogen and with the reduction of temperature, when it converts to para hydrogen, causes evaporation of hydrogen, this process is known as boil off. And what is required is that this boil off should be as low as possible. So we need to minimize this evaporation in the storage tank, and thus we need to minimize this ortho para conversion, which is very important when we are considering long term storage. The reason being, if at normal temperature pressure hydrogen, if it is very fastly cooled, in that case the hydrogen may convert or may liquefy, but then in that case the concentration will be again same as the normal hydrogen, and when it is being stored at that temperature 20 Kelvin, then slowly this ortho to para conversion will occur, will release heat, and the liquid hydrogen will start to evaporate, and that will be resulting into boil off loss. Also we need to understand that ortho to para conversion, this process is a very slow process. This is a second order reaction which takes place very slowly, and it can take about several days or a week time to convert without catalyst from ortho to para. Now if we want to increase the rate of this conversion, we have to use a catalyst. In the presence of catalyst, depending upon what catalyst, what is the temperature, what is the pressure, this conversion is a first order reaction. However, at the liquid hydrogen temperature, at 20 Kelvin, this conversion is a 0th order reaction and takes place very fast. So, once we have cooled down the system to liquid hydrogen temperature, in that case this ortho to para conversion takes place very fast and is an exothermic reaction leading to boil off, and that is not required when we are storing hydrogen for long term, because that will result into evaporation of hydrogen and then we will have to release that hydrogen which is evaporated. So, liquefaction process have ortho to para conversion, and most of the cycles, liquefaction cycles, they have this ortho to para conversion systems, and that reduces the boil off. Another important characteristic that we need to consider in liquefaction of hydrogen is throttling. Now, throttling we have studied in more detail. What is the Joule-Thomson effect, what is the Joule-Thomson coefficient, when is it positive, when it is negative. Now, important when we are liquefying hydrogen is the throttling, which is common to most of the cycle, and this is created after we create a sort of non-ideality, and this non-ideality condition is carried out by either increasing the pressure by compressing or lowering down the temperature, that is pre-cooling, or it can be done using both. Now, the problem with gas like hydrogen is its inversion temperature is below ambient, and if we want to get the maximum cooling effect, we have to cool it down below the maximum inversion temperature, so that we can get a maximum cooling benefit. As such, because of this inversion temperature being below ambient, pre-cooling of the gas becomes essential, so that it can be cooled down before throttling below its inversion temperature, and then only we will be able to get a cooling effect on expansion. So, pre-cooling becomes essential because of the negative inversion temperature of hydrogen above the ambient temperature. If we look at the hydrogen liquefaction process, then before 1895 the process which was considered was compression followed by chilling, reduction in the temperature, and finally an expansion by means of throttling. So, prior to 1895 this was the process flow that was followed. Herein the working media used to be hydrogen, and the saturated vapor was not returned as a coolant after the throttling. So, after the throttling process that we will see in the subsequent slides, that after the throttling a certain amount of liquid will be obtained, however vapor will be at a lower temperature. So, that vapor which was formed after throttling, that was not returned back as a coolant into the stream. But after 1895 the recuperative cooling was employed, and here the liquefaction fluid that was itself acting as a coolant. Now, if we look at the process thermodynamics, we have also studied earlier, the thermodynamic effect which is used for expanding is that we do an adiabatic expansion. So, if we look at the complete process, it should be an isothermal compression and an adiabatic expansion. So, expansion is adiabatic. Now, this adiabatic expansion can be done either by mechanically extracting the energy from the fluid which is being expanded. So, the fluid which is being expanded, from there the energy is extracted mechanically, then the process is isoentropic process, and the component used is an expanding machine or an expander or an expanding device. However, if this extraction is not done, so without extracting the energy, in that case the process is isoenthalpic, and that is what happens in the throttling process. So, if we quickly see what are the processes or what are the steps that occurs in hydrogen liquefaction is, first of all, since finally we have to do an expansion, we have to increase the pressure so as to expand. So, first step involved is a compression step, where the hydrogen is, the gaseous hydrogen is compressed to a higher pressure. This higher pressure should be such that it should be higher than the critical pressure. Thereafter, once compression is done, cooling is carried out to reduce its temperature. Now this cooling can be done in 2 steps. First is a pre-cooling. So from the temperature ambient or after the compression, it will be at a higher temperature. So from the ambient or to a higher temperature, we have to cool it down to 80 K or slightly higher or lower temperature, depending upon that, depends on several other parameters. That means liquid nitrogen cooling is done, which is also known as pre-cooling. The another step could be a final cooling. So this is at a temperature which is much lower than the liquid nitrogen temperature, and that can be achieved using recuperative cooling, where the vapor after throttling itself acts as a coolant. And finally the step involved is an expansion step, where the gas which is at a higher pressure pH, it is expanded to PL using the Joule-Thomson valve. In this process the hydrogen partially gets liquefied, and that amount which is getting liquefied is collected. So the liquid hydrogen in this process which is obtained can be collected. The remaining which is in the vapor form or the vapor fraction of the gas which has got liquefied, or the flash gas, also known as flash gas, this is allowed to exchange heat in a heat exchanger in such a way that it cools down the hydrogen stream in a heat exchanger, and finally it is again fed back to the main stream, to the feed stream before compressor. So in general these are the 3 major steps which occurs in hydrogen liquefaction. Now there are several ways of doing that, there are several components which can be used depending upon what are their energy consumption. We can have, even to reduce their energy consumption, we can have complicated cycles, we can have cascading, hybridization. So we will see all those cycles now. So for large scale liquefaction, the well known cycles are the simple Claude process, Kapitza process which is a modification, it can be a dual pressure Claude process, it can be pre-cooled Linde-Hampson cycle, or it can be pre-cooled dual pressure Linde-Hampson cycle, it could be helium pre-cooled Claude cycle, or a pre-cooled mixed refrigerate cycle, or cascaded cycle. So these are several options depending upon what are the components used, they are in fact classified into these type of liquefaction methods. Starting with the simple Claude cycle, here if we see how the liquefaction occurs, the gaseous hydrogen, it is compressed in a cooled compressor. So there is an intercooling involved in the compressor. So the gaseous hydrogen undergoes this gaseous hydrogen undergoes compression, then it goes through a series of heat exchangers such that its temperature reduces. Finally it undergoes throttling. Now between one of the heat exchangers is an expander or an expanding device. So what happens is, the part of the compressed gas, it goes through an expanding device reducing its temperature, and that gas which is cooled then mixes with the hydrogen stream, returning hydrogen stream. In that way the temperature of the gas further cools down. Now this expander or this expanding device cannot condense, because if it condenses then that is detrimental for the hardware. So it only lowers down the temperature of the gas. Now in this process it undergoes, the gas, compressed gas passes through a number of heat exchangers reducing its temperature below the inversion temperature, which is the requirement for the throttling process. Once its temperature reduces below the inversion temperature, it passes through a throttle valve, undergoes expansion such that certain amount of, a small amount of liquid is or gas gets liquefied or liquid hydrogen is obtained. Now in this vessel the liquid hydrogen is collected while the gas which is not liquefied or is still in the vapor form or the vapor fraction of this gas is further recirculated back through these heat exchangers, so that it can reduce the temperature of the feed gas stream to the throttle process. Now once it has exchanged its heat with the feed gas, finally it is fed back before the compressor. So this is how the process takes place. Now this expansion device which is used before the throttling process is to reduce the temperature of the gas. Now if we see thermodynamics of this simple Claude cycle, now we can do the energy and mass balance. Considering the different points, we can do the mass balance of the control volumes. So the gas, it enters into the compressor, leaves the compressor, goes into the heat exchanger, and the same goes into the expander. After the heat exchanger 2, after the heat exchanger 3, goes to the throttle valve, certain amount of the gas gets liquefied, the remaining still is in the vapor form, that again goes back to the heat exchanger. Now this, at this point it gets mixed with the gas which is coming from the expander, and as such this is 0.8, 9 and finally 10. Now if we write a mass balance for the control volume at steady state, so at this point after the compressor M2 dot is equal to M1 dot, and let us say it is M dot, this is the first equation. At point 3 this is same as ME dot after the expanding device, so after the expander. Now the gas which is at the exit at point 10, M10 dot is it, this is M1 dot which is entering and some amount which has already been liquefied. So M1 M10 dot is M dot minus MF dot. So the amount which gets liquefied is subtracted, and this is M dot minus MF dot, because M1 dot is same as M dot. Now M dot is in general represented for the mass flow rate of stream X, and this is expressed in kilojoules per second. Same we can write the energy balance between the different outlets. So the energy balance is written at the outlets of compressor, expander, considering the different components, compressor, heat exchangers, expander and separator. So the energy balance is M10 dot H10 plus M3 dot H3, MF dot HF, and that is equal to M dot H2 plus ME dot HE. Now if we substitute these values, for M10 dot it is M dot minus MF dot H1, because H10 is H1, considering H10 equal to H1. So this is M10 dot H10 which is M dot minus MF dot H1, M3 dot is ME dot, so ME dot H3 plus MF dot HF, and that is equal to M dot H2 plus ME dot HE. So this is the energy balance where H is specific enthalpy of the stream. Now if we see how much is the mass fraction at the expander, this is at the expander. So the mass fraction at the expander, which is E, which is exiting from the expander, in that case the ratio is ME dot over M dot, and the amount of which get liquefied or the liquid yield is given by MF dot upon M dot, and that is H1 minus H2 upon H1 minus HF plus X times the mass fraction at expander times H3 minus HE divided by H1 minus HF. We can also calculate the net work which is required per unit mass of the compressed gas, and this is the net work or the net energy consumption in the cycle W, which is expressed in kilojoules per kg, and this is given by the net power consumption in the cycle divided by the mass flow rate, and that is equal to temperature T1 S1 minus S2 minus H1 minus S2 minus X of H3 minus He, where the S is standing for specific entropy of the stream X, and that is kilojoule per kg Kelvin. We can also calculate the specific energy consumption, which is expressed as the energy consumed divided by the mass which gets liquefied. So, the energy consumption per unit mass liquefied, it is in kilojoules per kg. This is W dot upon mf dot, and that is W dot upon m times y from this expression. Mf dot is y times m dot. So, the specific energy consumption is the power, net power consumption divided by m dot y. So, the y is the fraction which got liquefied and the mass flow rate. We can also find the coefficient of performance, that is the cooling which is provided by the working fluid to the net input power in the cycle. So, that is the COP, and that is given by m dot times the enthalpy of the feed minus HF of the liquefied hydrogen divided by the net power consumption. Now, this was the thermodynamics or the energy consumption in a simple Claude cycle. There are several variations to the simple Claude cycle. The variation to simple Claude cycle is the Kapitza process, wherein we can use reciprocating expansion engines instead of that expander. So, that expander is in fact the reciprocating expansion engine, and this particular process is specially used when large scale hydrogen production is required. We can also have dual pressure Claude process. So, instead of one pressure, compression to one pressure before a throttling, we can have two pressure levels or two compressors being added. This is because the minimum work is proportional to pressure ratio. So, minimum work in compression, that is proportional to the pressure ratio and not the pressure difference in the cycle. Now, we also know that the compression energy, this varies with the logarithmic of the compression ratio. For example, if it is a simple Claude cycle with a primary compressor, with a compressor having a compression ratio of 200:1, we can get the logarithmic value of 5.3 as the compression energy. So, that logarithmic term is 5.3. However, if we use a dual pressure cycle or a dual pressure Claude process, then this compression ratio, there are two compressors. So, the main compressor that will have a compression ratio of 200/5, and that can reduce the logarithmic term to 1.8, and that clearly shows the improvement in the performance and the energy consumption reduction. Now, in an ideal simple Claude cycle, the pressure as it increases, the minimum work of compression that reduces, and as we know, because it is proportional to the pressure ratio, and then the expander flow rate is corresponding to the minimum work, that also reduces. But the major problem with the Claude process is, because we are using several components, there is a expander which is being used, there are several heat exchangers being used, in fact 2 heat exchanger in the simple Claude process, that adds up to the capital cost of the simple Claude cycle. So, the next cycle we will see will be the Linde-Hampson cycle, which compared to the Claude cycle has a lower capex, capital investment, but compared to Claude cycle it has a higher operational cost. So, operational cost of Claude is lower compared to the Linde-Hampson, the reason being the lower power consumption in the Claude process. So, we have seen that in the Claude cycle there is a expander or an expanding device which is used, but the Linde-Hampson cycle that has a pre-cooling step which is by means of liquid nitrogen, and this pre-cooling step is introduced, the reason because the inversion temperature of hydrogen is below the ambient temperature. So, that becomes inevitable. So, it can be either by means of an expander, which is done in case of the Claude cycle, while in case of pre-cooled Linde-Hampson cycle, this is by means of a liquid nitrogen system. Through a heat exchanger, the hydrogen is being cooled. Now, in the addition of this pre-cooling not only reduces the temperature of hydrogen below its inversion temperature, but it also improves the yield of liquid which we are getting. So, the yield of liquid hydrogen which is being collected. This is because it improves it decreases in fact the enthalpy of high pressure gas at the warm end of the heat exchanger. So, this reduces the enthalpy of the gas which is entering into the heat exchanger by cooling that. And also the high pressure which is required, the requirement of high pressure can still be reduced if we cool it down, we pre-cool it using a liquid nitrogen network, and this can be done by reducing the temperature before it undergoes the throttling. So, inclusion of this liquid nitrogen cooling has several benefits. It reduces hydrogen gas temperature below its inversion temperature, it reduces the enthalpy of the gas entering in the heat exchanger. At the same time, it reduces the pressure requirement before throttling. Now, the pre-cooled Linde-Hampson cycle is where the gaseous hydrogen, it gets compressed in a cooled compressor. Once it is compressed, it passes through a heat exchanger wherein its temperature is dropped below the inversion temperature by means of liquid nitrogen cooling. After that, it is throttled through a Joule-Thomson valve, undergoes an isoentropic expansion. In this process, some amount of liquid hydrogen is formed which is being collected. The remaining which is still in the vapor form, that is allowed to exchange heat, or that itself acts as a coolant, cooling down the inlet hydrogen gas stream from the compressor to the throttle valve. So, in the way back to the compressor, that passes through the heat exchanger and undergoes, or it acts as a coolant for the feed gas to the throttle valve. After this heat exchanger, it is fed back to the compressor. So, this is the simple pre-cooled Linde-Hampson cycle. Now, performance wise, this pre-cooling improves the performance of the entire process, and we have seen the various reasons why it improves the performance. Now, if we compare the Claude cycle with the Linde-Hampson cycle, the specific energy consumption for a ideal Linde-Hampson cycle is 16.24 kilowatt hour per kg, but for Claude cycle it is 22.1 kilowatt hour per kg. So, it is less in case of Linde-Hampson cycle. Now, this performance can further be improved if instead of one stage compression, if we include two pressure levels before throttling. So, we can have two pressure levels included, and then it becomes dual pressure pre-cooled Linde-Hampson cycle. And the energy requirement can be reduced not only by means of pre-cooling, but by increasing one more component, the one more compressor, and then we can have dual pressure levels included. Now, if we consider that dual pressure ideal Linde-Hampson cycle, then the specific energy consumption it reduces to 12.12 kilowatt hour per kg of liquid hydrogen being produced. While if the same we apply to dual pressure we apply to the Claude process, it reduces to 6.66 kilowatt hour per kg. There are many other cycles which are possible. There are several other variations, like one of the variation is Collins process, wherein we have further added one more expander, and then there are a series of heat exchangers which have been employed in the process. Now, other variations to the pre-cooled system, this is for the pre-cooled system there are many variations possible. One is like helium pre-cooled. Now, we know that the major component of the cost is also a compressor in the liquefaction system. Higher the size of compressor which is being used, higher will be the cost associated. Now in order to reduce the size of compressor, then the flow rate will also reduce, the pressure will also reduce, and that can still work well if we use helium for pre-cooling. So that helium acts as a working fluid here and the cycle becomes helium pre-cooled cycle. Another possibility is the Joule-Brayton pre-cooled cycle, where again helium cycle, it acts as the helium system, it acts as a refrigerant, while the final expansion, this is done by means of an expansion engine. And this working fluid, this is not liquefied, however its temperature is reduced to below the hydrogen temperature. Another possibility is with the use of different refrigerants, and then we can have mixed refrigerant pre-cooled cycle. So there can be mixtures of gases and vapors which acts as working fluid in the refrigeration cycle. Now this mixed refrigerant cycle, that acts as a pre-cooler for the expansion for the remaining cycle, or we can superimpose, or we can have a hybrid. So we can have a cascaded system wherein different independent cycles, they pre-cool the other refrigeration cycle, and with this particular system it approaches very close to the ideal reversible liquefaction process, reducing the net amount of energy consumption. But as we keep on adding the different components, the complexity of the entire process increases, and this cascaded system is especially important when we have to use it for wide temperature range, and there it improves not only the yield of the liquid which we are getting, but also it improves the efficiency. So to summarize this part, there have been several hydrogen liquefaction plants which are operational in the world. These are located in various regions, it is in USA, Japan, Canada, Holland, France, China, Germany, India. Now if we see some of these representative examples, like the one which is being installed by Praxair, this is having a specific energy consumption between in the range of 12.5 to 15 kilowatt hour per kg. Another one in Germany, Ingolstadt, that has 13 to 15 kilowatt hour per kg of specific energy consumption. The plant that has about 13.5, that is 4.4 tons per day of hydrogen being produced, liquid hydrogen being produced, and it operates on the principle of pre-cooled Claude cycle. This specific energy consumption is still very high. The US DOE targets are to achieve a specific energy consumption of 6 kilowatt hour per kg for a large sized plant of 300,000 kg of hydrogen liquefaction per day, and still it is way far off compared to the plants which are operational today. So we have to reduce, the requirement is to reduce the specific energy consumption because the liquefaction is a highly energy intensive process. We have to reduce the energy requirement, and that can be carried out by several process integrations and many improvements in the cycle. But with integration, processing integration, including more and more components to reduce the specific energy consumption, the entire cycle becomes more and more complicated. Out of the total liquefaction cost, considering a size of 100 tons of liquefaction per day, about 40 to 50% is the capital cost involved in the plant. So there have been improvements, there have been models wherein large size plants have been modeled and also developed, like a size of 50 tons per day with liquid helium cooling, and that had 4 ortho to para converter systems, which has reduced the specific energy consumption to 8.73 kilowatt hour per kg. Another one which is being modeled is pre-cooled Claude and Joule-Brayton cycle, and that has a specific energy consumption of 5.85 kilowatt hour per kg. So as we are looking at the reduction in the specific energy consumption, the process gets more and more complicated. Then 4 Joule-Brayton cycles being cascaded together, and then used the mixed refrigerant cycle as well for the refrigeration, and that reduces the specific energy consumption to 5.35 kilowatt hour per kg. So the major challenges which we can see with the liquefaction processes, the high capital cost, the high specific energy consumption, boil off losses, inversion temperature of hydrogen which is in fact lower than the ambient temperature, conversion from ortho to para, all these leads to a complicated hydrogen liquefaction process. Thank you.